right. Well, this is going to be the review for the test coming up this Tuesday. Now, I've got the pre-test solutions written up. I'll send those. I'm going to try to get this sent out tonight. I'm going to mostly do problems not on the pre-test, because once you have the solutions, well, okay, you know how to do that problem. And I figured, well, why do some different problems to kind of mix things up a bit or give you more options. The one thing I do want to point out on the pre-test, though, is question number 1. And if you look on page 678, you have guidelines for verifying trigonometric identities. When I was looking at number 1, that looked like a tricky problem, because looks like what you want to do is make this numerator into this numerator, and this denominator into this denominator. But you actually can't do that. The trick with this one, I'm going to start with this side. And starting with this side, we need to introduce this as a denominator. We need to somehow get it in there. And the way we can do that is that we can multiply top and bottom by this denominator we're looking for. So I'm going to try to make this side look like this side. So, I mean, good luck. You can't really turn this into that. So I'm going to introduce it, in a sense, kind of artificially. This is one of those cases where, okay, I don't really know what I need to include so much, or I need to include something new is what I should say. Ideally, we like to take a complicated thing, break it down into the simpler side. Complicated side, break it down into the simpler side. This case, though, we got to bring something in. We do have to bring something in. I'm going to multiply top and bottom by secant t minus 1. And this is what we're going to get. Now, what happens on top, we're just going to have to figure that out. We do have at least the denominator that we're looking for somewhere in this expression. That's about the best we can do. Let's simplify things and just see how it turns out. So if you FOIL these two, what you're going to get this. Now, here you want to break out your knowledge of the Pythagorean identities. So, recall that 1 plus tangent squared theta equals secant squared theta. So what we can do, subtract 1 from this side. Now, why am I doing this? Well, I'm not really concerned about this because there's no squared. There is a squared on this one. And if I can turn this, which is this right here, into tangent squared, I have a tangent into tangent squared, that's going to give me the other side that I want. So we're going to replace this with tangent squared t like so. We can divide tangent into tangent squared. We'll get tangent t over secant t minus 1. And that's the other side we were looking for. So what ended up happening is we had to introduce the denominator that we wanted and then simplify things down kind of on a leap of faith. But then keep that knowledge, that familiarity of your identities. And that's going to help you solve these. It's like, oh, okay, secant squared here and a minus 1. That might be one of those Pythagorean identities. That seems familiar. And then, sure enough, that's going to help you solve this problem or verify the identity. So I just want to go over that one from the pretest. Another one I want to go over. So question 18 on the homework. So question 1 comes from section 6.1. So question 18 from the homework, that is going to come from the section 6.5. So we're going to jump ahead a little bit. The version of it that I have is this. So again, this is section 6.5, and we're solving for x, where x is between 0 and 2 pi. So what I'm going to do, I'm going to let alpha equal 4x. So that means cosine of alpha is equal to 1/2. So let's think of all the angles alpha that where you take the cosine of those, you're going to get 1/2. And let's think about them in the unit circle. So cosine of what angles give you 1/2? Well, looking on your unit circle, you'll get pi over 3 and 2 pi over 3. Oh, no, not 2 pi over 3. I'm sorry. Give me a second. 5 pi over 3. Should be right. Yes. So pi over 3, 5 pi over 3. So that's what your alpha is going to be. Now, technically, and this is something we just want to always do, we're not just going to say these two angles. We're going to tack on the possibility we have, say, a rotation and then our angle. That'll get us in the same position on the unit circle. So our alpha, it can be pi over 3 plus how many rotations? You have 2 pi is 1 rotation, n, so you have multiple rotations, and n is going to be an integer. So if it's positive, it's counterclockwise rotations. If it's negative, clockwise rotations. And then 5 pi over 3 plus 2 pi n. So again, we have the possibility of rotations. Now, this is what alpha can be. But we're not looking for this alpha. We're looking for 4x. So since alpha equals 4x, let's work with this first solution. We need to solve for x. So we're going to divide everything by 4. And if we do that, we'll get x is pi over 12 plus pi over 2 times n. So now we finally solve for x. Well, sort of. If we had a situation where we wanted all the possible solutions, all the possible angles, all infinitely many of them, well, we just leave things like this and say n is an integer, and you choose any integer you want, put it in there, and there you go. You can come up with an angle. But we want to be specific. We want x to be any angle that works between 0 and 2 pi. We don't want everything. You don't want to forget this one either. But we'll get to this later. So if we let n be 0, get pi over 12 plus 0. That's one of our answers. Now let n be 1. Pi over 12. Now pi over 2 times 1 is pi over 2. If you add these together, common denominator would mean multiplying top and bottom by 6. So you would get 7 pi over 12. So n is 2. Make n is 2 be pi over 12 plus pi. So top and bottom multiply by 12. 13 pi over 12. N is 3. Three pi over 2. Let's see here. Got to multiply top and bottom by 6. Get a common denominator. 18 pi over 12. 19 pi over 12. Quite a bit. And then let's go n is 4. Will be pi over 12 plus, and if we make it 4, we're going to get 2 pi here. But now we've already gone too far. 2 pi is our boundary. We're not even supposed to get the 2 pi. So let alone being 2 pi, let alone being more than 2 pi. So for this one, where x is pi over 12 plus pi over 2n, these are the 4 valid answers we're going to get. So first off, and this one's got quite a few answers. Let me double check real quick here. All right. So that's the first set. Next set. So we have pi over 12. The next one, 5 pi over 12 plus pi over 2n. Well, here, let me start from the beginning. So for the other result, alpha is 4x, and we have 5 pi over 3 plus the rotations. Again, divide everything by 4. And so far, that's what we've got. Now, again, same thing. If we want all the possible answers, you just leave it like this, say choose n to be an integer, and then there you go, you're good. But we want to make sure we have angles that are specific. And these are the angles from 0 to just short of 2 pi. So we got to start breaking down ends, choosing ends. So if we let n be 0, well, of course, we get 5 pi over 12. And again, we're choosing positive ends because, again, our angles from 0 to 2 pi, so no negative angles. So when n is 1, we have pi over 2. Again, common denominator, multiply top and bottom by 6. We have 11 pi. 12. Now for n is 2. If we multiply pi over 2 by 2, we're going to get pi. Now again, multiply top and bottom by 12 and get that common denominator, about 12 pi over 12. So that'll become 17 pi over 12. Finally, for n is 3, well, maybe not finally. So multiply top and bottom by 4. No, I'm sorry, by 6. So 18, so you get 23 pi over 12. Finally, and it's going to be finally, it's 5 pi over 12. 4 times pi over 2 is 2 pi. So once again, we're overshooting our boundary, so we can't do that. So what are our answers? Well, the answers are these and the answers we got before. So for this problem, you're going to have 1, 2, 3, 4, 5. I'm sorry, 1, 2, 3, 4 times 2. You're going to have 8 answers for this problem. So just keep in mind, sometimes they can get like that. Anyway, so that's we looked at a problem from 6.1. We did something from 6.5. Let's take a look at something from 6.2. Let's see here. Well, let's take a look at number 45 in 6.2. So we're talking about sum and difference formulas. And the thing for the test is that if you look at the pretest, there's some type of identity that has a half angle formula, a double angle formula, a sum and difference, a product to sum, a power reducing. There are different types in here. Pretty much all the different types of identities show up here. So you want to kind of, be familiar with those identities. Now this is going to be sum and difference. So let's go with this one. We want to verify this right here. So again, we want to be familiar with those identities. So we go, okay, cosine of plus, cosine minus. So what I'm going to do here, I'm going to start with where it looks like we can make a substitution for sum or difference identities. We do have a formula for this. We do have a formula for that. And if we insert those formulas, it's going to make things a little more complicated and give us more to work with. So let's do that. So cosine alpha plus beta. Cosine alpha, cosine beta. Minus sine alpha, sine beta. Times, because we got a multiplication here, cosine alpha, cosine beta, plus sine alpha, sine beta. So I'm going to work with this left side or this top part here. So again, we're going to FOIL this. So foiling it, first, multiply these two. Outer. And then our inner, and these are going to cancel out, but I'll go through the steps here just so you can see it. So you can see that this and this, those are going to cancel out. Finally, the last terms, these right here. So now we take into account the cancellations. Let's see here. Now this one's kind of tricky. What do we do for this one? Well, taking a look at where we're headed, on a cosine beta, we want to have a sine alpha. So we want to save these two. How can we get rid of the others? Let's see. Let's see just yet. Check. What can we do here? Do this. Well, we can't factor anything out. What we could try to do is convert one of the cosine squares into a sine squared. So we want to get rid of this, and we want to get rid of that. So I'm going to take kind of a stab in the dark. Use the fact that sine squared alpha 1 minus is cosine squared alpha. And 1 minus cosine squared beta is sine squared beta. So let's see what happens here. So if we distribute accordingly, we'll get cosine squared beta minus sine squared alpha cosine squared beta minus sine squared alpha plus sine squared alpha cosine squared beta. And now what we might see is a cancellation. This and this, those are going to go away. And what that's going to leave us with the very thing we're looking for. So I'll be honest on little you saw what happened. I got stumped. So the next step recourse, the next thing I can think of is, well, can I do something with the things I want to get rid of? So we got a cosine squared alpha, cosine squared beta, sine squared alpha, sine squared beta. We want to keep these two. We know that because that's what's on that right side. Is there something we can do with this or this that might change things up? Now, if you have a real head for algebra, I guess. You could think, well, if I made this a 1 minus sine squared and this one here a 1 minus cosine squared, I'll get those middle terms to cancel out. But if you're sort of like me, you don't have that head for algebra, well, what you can do is experiment. Write it down on a piece of paper and see if it works. And it worked out this time. Now, what if this doesn't work? Well, we still know what we want to hang on to. Maybe there's something else we can do, like maybe some other substitution we can make with these things that we don't want to have around. There might be different approaches to this. So that would be one way of doing this problem, though. Looking at what we want to keep and trying to think of a substitution for these things we want to get rid of that might allow for some cancellations and, well, leave us what we want. There is one other thing. I might want to consider one other possibility. Let's see. If I want to keep these, just thinking of a factoring approach, but not really seeing it. So what I'm thinking of is you pull cosine squared alpha out, you have cosine squared beta minus sine squared alpha, sine squared beta over cosine squared alpha. And that's not going to combine. It's tempting to call this a tangent, but because of the different angles, we can't do that. It's hard to tell, but that's an angle beta, that's an angle alpha. So that's not going to get us anywhere. So in this case, replacing the things that we didn't want with other expressions gave us something we could simplify and leave us with this in the end. All right. So we'll go with that for now. So let's take a look at 6.3. All right. So cotangent of x over 2. Wow. So for this one here, it might help. And since we're looking at 6.3, now you wouldn't know this on the test, but if you're dealing with a half angle formula, I think what I'm going to try to do is rewrite this as cosine x over 2 sine x over 2. The reason I'm going to do this is we don't have a formula for cotangent. That we simply don't have. So I'm going to break it down into formulas we do have. Cosine x over 2, sine x over 2. And let's see if this is going to make a difference. So our half angle formulas for sine, this is what's in the text. We use alphas. And then plus. Now, is this going to help? We could try taking the ratio of these two. Let's see what that does. Well, that gives us a cosine of x instead of x over 2. So we've gone from this to this. So far, so good. Let's try this. Double check, make sure we got those correct. Okay, looking good. Now we can combine the square roots. Now, is this going to do us any good? Well, let's keep in mind, this is sine x and 1 minus cosine x. Now this will become like so. Do our KFC with fractions. So is this going to get us anywhere? Hard to say. Now there is something we can do here. We could do this. Now let me check one thing with this problem, because there's going to be an issue with the signs, the plus and minus. Okay, there's no statement for that. All right. So we've got something like this. Now if we recall where we're going, we definitely don't have a square root. So one thing we could do is this. We could take 1 minus cosine x and multiply bottom and top by 1 minus cosine x. That'll give us 1 minus cosine x quantity squared. And since we're taking the square root, well, that'll get rid of the square root because the square and the square root will cancel. So we can do something like this. So what we're going to have and granted, I might not have an algebra brain, but I am a little familiar with one thing in algebra. If I have 1 plus something times 1 minus something, that's that formula for a difference of squares. My answer is going to be this squared minus this squared. Now that sounds like a Pythagorean identity. In fact, it is. So it doesn't hurt to sort of call back some of those algebra skills. And granted, there's so many, but one that seems to have been very helpful so far tonight is recognizing 1 plus times 1 minus, or alpha plus beta, alpha minus beta, that kind of thing. That sets up this Pythagorean identity. So just a little trick to keep in mind. So as we do that, If we FOIL this, sure enough, we'll get cosine x squared. Or 1 minus cosine squared x. These are canceling. So we're going to get plus or minus. Now 1 minus cosine squared x is sine squared. Ah, so this is working out. And sure enough, take the square root of the top and the bottom. What are we going to get? Sine x over 1 minus cosine x. So one of the issues with this is this plus or minus, and there was nothing specified in terms of what angle x should be. So cotangent, the typical domain for a cotangent, we usually take it as a, say, 0 to pi is the canonical domain for it. But can we do something with this plus or minus? Well, in terms of the first quadrant, this will always be positive. So let's think about this. Q1 sine x is positive, cosine x is positive, and 1 minus cosine x will be positive also. So everything here is going to be positive. Now, if we go to the second quadrant, quadrant 2, sine of x is negative. 1 minus, oh, I'm sorry, no, it's positive. 1 minus cosine x. Well, that's going to be negative. But 1 minus a negative is a positive. So again, it's positive. So in that quadrant, it's also going to be positive. Now let's see what happens in the third quadrant, though. In the third quadrant, sine of x is negative. 1 minus cosine x. Well, again, that's negative, but negative minus negative is positive, but negative divided by positive is going to be negative. So taking a look at this, let me see, what should we do with the plus and minus? Now, this one I might have to get back to you on. Do a little analysis on this, see if I can figure out what's going on here. Because the plus and minus does seem to be significant. And as we see on our, oh, well, that probably shouldn't be a problem. What you could say is, as long as our left side and right side are positive at the same time and negative at the same time, we should be all right. So that would be one argument. Is that actually going to be the case? Again, taking a look at this. The reason you might not have to keep the plus and minus, if you have a minus here, that means this is actually has the wrong sign, and you have to put a minus here to make it positive. So example, if this is positive, but this was the same quantity but negative, you'd have a minus sign here to clean it up. So this becomes negative also. If this is negative, and this for some reason came out positive, you need that minus sign to make this side negative. So one thing you could consider in this is, do you have to actually do that? So if x over 2 is, say, an angle in the, I don't know, let's say, let's go with a tricky one, say the third quadrant. If you double an angle in the third quadrant, where do you end up? Well, you'll end up somewhere between 2 pi and 3 pi, because your third quadrant so if our x over 2 is pi and x over 2 is 3 pi over 2, well, doubling that would put you from 2 pi to 3 pi. And as we've seen, if you're somewhere from 2 pi to 3 pi, or in the first or second quadrants, well, this is going to be positive. And for this one, cotangent from pi to 3 pi over 2, well, what kind of, what's that going to give you? And that's also going to be positive. A little bit of analysis here. If you think of the graph of cotangent, there's 0, pi, 2 pi. Cotangent is something like this. This is 3 pi over 2. So if we have this angle somewhere in the third quadrant, it's going to be positive. This would also be positive. If we have an angle, oh, let me see. So this is in the, I'm sorry, if you choose, no, so this, yeah, that's correct. If this is in the third quadrant, the angle over here is going to be from here to here, which is first quadrant and second quadrant, which we just saw was positive. So that works. So that kind of analysis, it's a little all over the place, but you can do that kind of analysis to see if you need the plus or minus. We haven't discussed much of that in class, so I'll be very careful about something like that on the exam because we haven't emphasized it as much. But be a great final exam problem, a quiz problem. We'll see. So what I might do is sit down and do a lesson on how to do that kind of analysis. Don't be afraid of figuring out your plus and minus. Well, let me do another one from this section that doesn't have the plus or minus thing in it. All right. So let's say we've got this. Let's go with a double angle. So let's say we're going to do something like this. We've got a sine of 2 theta. This we can break up. There is an identity for this. So what we can do here is, let's take this. Let's FOIL this out. Now, if we FOIL it out, sine squared theta plus sine theta cosine theta plus sine theta cosine theta plus cosine squared theta. So this is the key thing. These we have two of. So that's going to give us our 2 sine theta cosine theta. These will combine to 1. And so we'll get 1 plus 2 sine theta cosine theta. And that's it. Now the key step here, this is something we have an identity for. We want to make things simpler. So turning your tangents into sine over cosine, your secants into 1 over cosine. And then if you recognize an identity like this, break this down. And it also helps too. We want to get everything in terms of the same type of angle if we can help it. So if we have a 2 theta versus thetas, we can turn this into single thetas. And that lets us move, not move things around, but gives us a more realistic target to aim for. So other than that, next question. Let's see here. Let's do, so in 6.4, let's do this. So let's say we have something like this. Boy, well, that's quite a bit. We're aiming for this. I'm going to put parentheses here just to emphasize we're taking the tangent of that. And let's see. Oh, I think I'm missing. No, that's all it. Double check. Just be careful when you do this on your scratch work. Make sure you write it down exactly as the problem has it, because it's a pain to go through all that work, get stumped, and you realize you're off by a term because you copied something down incorrectly. That can happen, like a minus sign. So just be careful when you set these up. So I'm going to check it. I got everything right. Looks good. So this is the sum and difference part. Now, one clue in this I'm seeing, I've got sums, but I've got a single term here. So I could go maybe a sum to some kind of a product. Let's see if that helps. It's beginning to glue things together. So on page 706, and another thing to be familiar with these, if you look at the sum and difference formula, or in this case, sum to product, sum to product, you have the bringing together of the angles in this kind of pattern. So again, that kind of familiarity, that where you see this kind of bringing things together of an angle plus an angle over 2, well, that's going to be your sum to product formulas. So for this one, when you're summing the sines, I'll start on this side. We'll get 2 sine x plus y over 2 cosine x minus y over 2. And then for this one, let's see, I have a sum of cosines to cosine x plus y over 2. And then we have a sine x minus y over 2. No, it's another cosine. I'm sorry. Another cosine. All right. So what can we do here? Well, again, our target is a tangent. It's an x plus y over 2. So we do have x plus y's over 2's. We do have a sine and a cosine. And when sine is over cosine, you get tangent. So this right here, well, this will become the tangent of x plus y over 2. Now, it doesn't matter what kind of angles we're dealing with. I mean, this is a complicated angle, and it's the same complicated angle as this. And, I mean, if you want to make things easier, call this one alpha, call this beta, call this beta, just to make things a little simpler. But if you're okay with doing things like this, well, we see this will be a tangent of x plus y over 2. Now, we need the other stuff to cancel out. Sure enough, the 2's go away. And the cosines, they're the exact same angle as well, with the same trig function. They're going to go away as well. And sure enough, we're left with the tangent x plus y over 2. All right. So let's see here. That's a product. That's a sum of product one. Now, some of these are fairly formulaic. Now, here's a good one, number 20. Now, something like number 20, it's going to be this. We're going to compute something. The cosine of 75 degrees minus cosine of 15 degrees. Now, before we got into trigonometric identities, this would be a bit of trouble because we don't have a 75-degree angle or a 15-degree angle on our unit circle. Now, since we do have a difference of cosines, we do know, if we're familiar with our the product formulas, that we're going to be doing something with combining these angles. And you might notice that if you did 75 minus 15, you would get 60. And then 75 plus 15 would give you 90. So those are going to be two familiar angles. So hopefully we have an identity that lets us combine these angles in those sorts of ways. And sure enough, if we take a look, we do. The difference of cosines is -2 times the sine of the sum of the angles, and then times the sine of the difference. More than minus sign. So we're going to end up in familiar territory. So -2 sine. Now, luckily, this is 90 divided by 2. Luckily, 90 divided by 2 is 45 degrees. So, okay, there's that little extra bit there, the division by 2. And then we have sine of 60 divided by 2, or -2 times the sine of 45, and the sine of 30. So now sine of 45 degrees, well, that's rad 2 over 2. Sine of 30 degrees is 1/2. And so what we're going to get is negative rad 2. You multiply those together. So okay, that's right. There's no questions, but all right. So going ahead to 6.5. Well, there's one other problem. Let me go back. Let me do one other problem that's on the pretest. Let me do one that's a little different, though. So let's say we have something like this. And we want the cosine of alpha over 2. Now, there's different ways to handle the cosine of alpha over 2. Let's see here. I mean, you could use a Pythagorean approach. Actually, no, you couldn't. I take that back. I'm sorry. No, we won't do that. But we do have this. Cosine of alpha over 2. Uh-oh, plus or minus again. So what is this going to do to us? Well, to come up with the cosine of alpha over 2, we need the cosine of alpha. Now we've got this plus or minus here. Which should we take? Well, we have alpha between 0 and pi over 2. So if we're thinking of this in terms of the unit circle, there's pi over 2, there's 0. So alpha is an angle between 0 and pi over 2. It's in the first quadrant. So because it's in the first quadrant, well, the cosine of all angles in the first quadrant is positive. So that means we're not going to have the negative. This will be a positive. Or alpha, I should say. Since alpha is between 0 and pi over 2, well, alpha over 2 is going to be the same thing. You can think of alpha over 2 as a little angle, sort of doing something like this, half of alpha. So since alpha is in the first quadrant, well, alpha over 2, we're just dividing by a positive 2. It'll be some half angle or going across like this. That's going to be alpha over 2. Again, it's going to be in the first quadrant. So that being said, this will be positive. So we can ditch the minus. Now we just need cosine alpha. Now cosine alpha, we use opposite, adjacent, hypotenuse. Now, here's the opposite. Here's the adjacent. Now, the bad news is with this triangle is we're not given the hypotenuse. So we got to figure that out. Now, to do that, we just use a Pythagorean theorem. The hypotenuse squared will be this squared plus this squared. Let me grab a calculator real quick. Let's see here. Pardon me just a moment. The sound of rummaging in the office. 24 times 24, 576. Plus 49. 625. And if we square root that, we get 25. So if we square root this, we're going to get 25. So the hypotenuse will be this. So let's go back to this cosine of alpha. So cosine alpha, cosine is adjacent over hypotenuse. The adjacent is 24, and hypotenuse is 25. So finally got our cosine alpha, we can plug this into this formula. So the cosine alpha over 2 will be the square root 1 plus 24 or 25 divided by 2. So we have this. Which will turn out to be the square root of 49 over 50. We can square root, you can leave it like, well, if you're going to do this properly, we square root top and bottom. Now, square root of 50 is square root of 25 times 2. Back up a little bit. Got to break up my square roots. Don't want to forget that. 5 square root 2. Square root of 25 is 5. Get the square root 2 though. We'll multiply top and bottom by square root 2, rationalizing our denominator. And so we get 7 root 2 over 5 times 2, or 7 root 2 over 10. Right. So you might get something like that. There's definitely one on the pretest. So let's take another one at 6.5. So let's say we've got this. Make sure this isn't one on the pretest. Looks a little familiar. I think it is. All right, we're good. So let's go with so we want to solve for x, and in this case, let's put x in this interval. Say we have something like this. So in this case, we do what's called a u substitution. We're going to let u equal the sine of x. So it makes it a little more easier to work with. If we do that, we get 2u squared minus u minus 1 is equal to 0. Solve for u. Use your quadratic formula. So negative 1 plus or minus the square root. Negative 1 squared minus 4 times 2 times negative 1 divided by 2 times a, which is 2. So negative b plus or minus the square root b squared minus 4 times a times c divided by 2 times a. So simplifying down. All right. So we're going to get two solutions here. We're going to have 1 plus or minus 3 over 4. So if you go with the plus, this will become 1, we'll get 4 over 4. Go with the minus, you're going to get that. So our answer for u, and that's all that we've done, we just solved for u, it's going to be 1 or negative half. Both of these are answers. Now remember what u was though. U originally was sine x. So that means sine x is equal to 1 and negative a half. Now remember, we want x's that are between 0 and 2 pi. So what are the angles between 0 and 2 pi that give us a sine of 1? Well, that's pi over 2. There's only one angle that does that. Now what about negative a half? Well, let's think about this on our unit circle. Let's see, if you look in the y-coordinate of the points on your unit circle, only 2 points will have sine values or y values of negative 1/2. Let's see. That would be 5 pi over 6. Now what would the other one be? 643, 346, 643, 346. That would be 11 pi over 6. So these here would be your 3 answers. Well, let's keep saying questions. If you have questions about this, let me know. All right. So I do actually, I've got a few minutes left. I do want to talk about that one problem though. Just go back to this one that we had. Because this wasn't something we talked about in class, and I think it's an important thing to discuss. So we want to think of this in terms of quadrants. So let's choose this to be some angle in the first quadrant. So it's something in there. So that means that angle is from 0 pi over 2. Now, the cotangent from 0 to pi over 2, what do we know? Well, for Q1, the cotangent is positive. So for Q1, that's what we've got. Now, if we double this angle, what are we going to get? Because now we're going to have double the angle and double the angle. So for x, we double this, we'll get 0 to pi. So now we can do our analysis. What's the sine of sine from 0 to pi? And again, look at your unit circle. The sine of x is positive. And then 1 minus cosine x. 0 to pi covers two intervals, or two quadrants, the first quadrant and the second quadrant. In the first quadrant, cosine is positive. In the second quadrant, it's negative. So it'll be positive or negative. But if you take whatever number is here and subtract it from 1, you're still going to get a positive number. If cosine is positive, 1 minus positive is going to be positive or 0. And we'd have to make sure that we have this defined so we don't get 0. For example, we would not want x to be 0. You get cosine of 0 would be 1. And of course, cotangent, you have to be careful because it has those asymptotes, vertical asymptotes. So not all angles are permissible. But moving on. So that's what that means. We're still going to get a positive. So as far as the first quadrant will go, cotangent will be positive, and sine x over 1 minus cosine x is going to be positive. So we don't have to have a correction sign. So if this was positive, but this came out negative, we need to put a minus sign in front to make it positive again. Well, if we're getting positive and positive, we don't have to do that. We're good. Let's take a look at the second quadrant for x over 2. So first off, Q2 will be pi over 2 pi. So what's happening to the cotangent in here? Well, the cotangent, use x over 2, is going to be negative. You have a negative cotangent from pi over 2 to pi. And again, now I'm doing this by picturing in my mind the graph of cotangent. Don't have to do that. You can look on your unit circle and take the ratio of the cosine divided by the sine, or the y divided by the x. And that'll show you if you're going to get negatives or positives if you use coordinates from points or angles pi over 2 to pi. So for pi over 2 to pi, if x over 2 is somewhere in here, we're going to get a negative cotangent. So what about x? Well, if x is twice whatever this is, so it's going to go from pi to 2 pi. So what's going to happen to sine x over 1 minus cosine x? Well, sine x, if we have angles between pi and 2 pi, this is the bottom half of the unit circle. So that's going to be negative. And then 1 minus cosine x, well, it's the same argument we had before. In the third quadrant, or I should put it this way, for x, the angles from pi to 2 pi, those are the third and fourth quadrants. In the third quadrant, cosine is negative. In the fourth quadrant, cosine is positive. So we're going to get something like this. But regardless, 1 subtract a negative will become a positive. 1 subtract a positive will also be positive as long as We don't have 1 minus 1. And we're not going to allow for 1 minus 1 because that would cause a division by 0. So no angle that causes that is going to be permissible. So this will be positive. Well, this is good news because sine of x, which is negative, divided by 1 minus cosine of x, which is positive, negative divided by positive is negative. So once again, if this is in the second quadrant, cotangent is negative, and that is also negative. So they match up. So again, we don't need a correction minus here to fix things. So far, so good. Everything's matching up. Because this is negative, this will be negative. If this was negative, but this was positive, you need to make it negative. You have to put that minus sign there. So let's say we're in Q3. Well, what's happening in Q3? Well, we're going from pi to 3 pi over 2. This x over 2 is. So that means the cotangent in this quadrant, if you take your x-coordinate and divide by your y-coordinate, you're dividing a negative by a negative. Your cotangent is positive. So now, is this going to come out positive? Let's find out. So the sine of x, well, first off, let me back up. We're going to double the angle to get x. So if we double this from here to here, but double it, we'll get 2 pi, 3 pi. So now we have what x is going to be taking on as angles. We can take a look at this. Sine of x. Well, from 2 pi to 3 pi. Well, that's really still the upper half of your unit circle. It's the same thing as going from 0 to pi. So sine of x is going to be positive. Now, what's going to happen to 1 minus cosine x? Well, if we're talking about the top half of the unit circle, that's really the first quadrant and second quadrant. And cosine is positive in the first and negative in the second. But again, if we're subtracting this from a number as big as 1, it's still going to come out positive, just like we've seen before. So that means sine x or 1 minus cosine x. Again, that's going to be positive. And the cotangent in this expression, they match up. We don't have to have a correction minus sign. Like if this was positive and this was negative, we need another negative in front to get the double negative effect to make it positive. So we don't need that correction negative. Finally, for the fourth quadrant. So it's in Q4. So x over 2 will go from 3 pi over 2 to 2 pi. That means cotangent. In this quadrant, in the fourth quadrant, what we have is again a positive x and a negative y. Divide positive by negative, you're going to get negative. So let's double things. If we double these angles, we'll go from 3 pi, 4 pi. This is the lower half of the unit circle. So when we're working in the lower half of the unit circle, sine x It's going to be negative. And then again, 1 minus cosine x. You'll get negatives, you'll get positives for cosine x, but when you're subtracting it from something as big as 1, it's going to come out positive. And so negative divided by positive is going to be negative. And once again, they're going to match. So that's how you can do an analysis on this, to see that as you do one rotation, in one full rotation, everything's going to match up. When things are positive, they're positive. When they're negative, they're negative. And then this will go on for multiple rotations as you repeat the same patterns. So, all right, any question? Oh, that's right, I keep forgetting, I'm just asking for questions. So there we go. Other than that, that's going to be the review for today. And if you have any questions, let me know, send me a message. And I'm going to send out the pre-test solutions, if not tonight, tomorrow morning. And yeah, let me know if any questions over the weekend. Other than that, have a wonderful, wonderful evening and good luck studying. And I'll see you on Tuesday if I don't hear from you before.